Okay, let's get started. Okay, so just a reminder, this is consistent with what I told you before, right? Yes? Okay, the final exam is BSF 166 Tuesday night, 7 p.m. Let me show you what I've posted for you on Blackboard. So if you go to exam prep, so I have attached final exam study tips. So I gave you a workbook practice list. So I made a long list of problems that will help you to hone in on the most important things we talked about in each module. Okay, module 2, module 3, 4, 5, 6, 7, 8, and then the module 10 stuff, the online stuff. Okay, so everything on the final exam relates to problems and ideas and concepts in this list. Okay, everything. So, but it's not problems like these with different numbers. So don't, when you're working these problems, you don't be in kind of, what do I need to do to get the answer mode? Rather, when you work these problems, what do I need to understand? What is this problem trying to teach me? Rather than what's the procedure I need to remember to get an answer? Okay, so that won't get you far, as you've learned very well in this course. So really ask yourself the right questions as you're going through these. What are the meanings of things? What's important? What are the quantities involved? How are the quantities changing together? And what's the relationship of how those quantities change? That's going to take you a lot farther than trying to remember methods. Okay? So there's that list. All the web work is still available for you to go, and then the answers are right there. So go back and relearn, rework, restudy web work problems. And then figure out what you're not remembering the most, and go back and all the class videos are available. All right, and what I'll do is we'll have on Monday, I'll have an open study session from 2 to 5. Or we should say, say 2 to 4:30. I'll put my office, but we may be in a different room if there's a lot of people. So just come there, look for a sign. If there's no one in that room that's my office, then look, there should be a sign on the door telling you where to go. Okay. The best use of this study session will be if you have already studied before you come, because then you'll have the answers and you'll have other students and myself to dialogue with. That's going to be your best use of this time. Not to start your studying Monday at 2. Okay, that's not going to be your best use of this. Do as much as you can over the weekend. Get study up as much as you can, and then you'll have and keep track of what you're not understanding, your questions, and then bring those here, and then that's how you really make the most of this study session. Okay? Yes, question.
What's the format of the test? Is it like formal?
Yep. Mm-hmm. It's like the exam, like the regular hour exams. Brendan.
And, how long will it take us, average?
The exam?
Yeah.
Most people will be done in less than 2 hours. Most people, but as long as we can stay around and the custodians don't kick us out, you can. It's kind of unlimited time. Kind of.
How many questions is it?
It's a little bit longer than the regular hour exams, so 35 to 40. Other questions? Okay. And then if also on Monday, if you want to look over old exams, you can look over old exams too, which would be another way to get ready for the exam. Okay? Any questions about final exam? Okay, so I noticed in the web work that there was trouble with this one. I left you a note. Hopefully, this should be really easy if we understand what vectors are, but there was low success, so let's do that. Let's do this one. So when you see a vector represented this way, with P, like 2 letters and an arrow over it, what I told you in note was that P is the location or the point of the tail of the vector, and you can see it's right under the tail, right underneath the tail, and then Q is where the tip would be. So it's saying that the point PQ, or P is -2, 3, -2, +3 is our point P, and then -4, there's -4 and 4, 5, 6, 7, something up like this is Q. So the vector PQ originates at P and terminates at Q. And how are we going to write the components of PQ? Well, we got to know what the components mean. What do the components of a vector mean? Are they coordinates? X and Y coordinates? Magnitude? No, not magnitude. Changes. Components are changes in horizontal or change in X and change in Y. That's why you can move a vector around and it doesn't change the vector. You can move it around. You still have the same change in X, change in Y. Okay? Vectors are mobile because they embody direction and magnitude, but not location. And that's because they're representing a change. They're representing a change, an overall change, and so we represent that as a change in X and change in Y. Okay, so if P is -2, 3, and Q is -4, 7, what is the change in X? How do you get the change in X from P to Q? This goes back to the first week of class. How do you calculate a change in a quantity? Final value of the quantity minus initial value of the quantity. So or you can just, in this case, you can just, if you're going from -2 to -4, what's your change in X? -2. Or you could do -4, the final, minus -2, initial. Okay? What about delta Y? It's the best vector I've drawn all day. Okay, so what is the change in Y? Starting at 3, ending at 7, right? So your Y coordinates started at 3 and you ended at 7. Change in Y is? You can just do that without even thinking, or you could do 7 minus 3, final minus initial. Okay, so I tried to explain that in the note, but still we had low success on this problem. Any questions? So it's all about the meaning of the vector components. Change in X, change in Y. So this vector PQ is the vector -2, 4. If P is at -2, 3, and Q is at -4, 7. And green bar. Any questions on that one? Okay, then the other one was number 7. Let's do that. Okay, so with these application problems, the key to these is change from polar form into component form, because with if you have multiple vectors that you're relating and adding and comparing, you got to have apples to apples, oranges to oranges, which means components. If you get all your vectors in X and Y components, then all the X components you can just add or subtract because they're all in the same direction. all the y components, you can just add or subtract because they're in the same direction. As soon as you have vectors in different directions, you can't add. You've got to have same direction. That's why using components is so helpful. Okay, so two poles are 12 meters apart. And the distance of sag is 4 meters. And so we've got 1 kilogram right here of mass. And so then this dimension here, so we can make a triangle like this. This right here is our 4 meters sag distance. And so this dotted line would be how long? 6. So we have a triangle forming there. Okay, so what's the tension on the ends of the clothesline? So we have vectors going on here. So we're going to isolate this point right here and talk about all the vectors at that point. What are all the vectors at that point? How many? And in this case, our vectors are forces, right? So we have forces. The force of this cable pulling this way. We have the force of this cable pulling this way. Is that it?
Gravity.
Yeah, so then the weight, there's the force of gravity pulling straight down on the point in the clothesline. So at this point, you've got these 3 vectors all pulling at that one point in the center of the clothesline. And so tension is a force. That's the scalar. Okay, so that's a scalar of force. So this is just the magnitude of force, tension, okay? And so we need what the force of gravity is on a 1 kilogram weight. So you might have to do a little research to remember your physics, that the force of gravity on an object is its weight, and that's calculated by mg, where m is the mass, in this case 1 kilogram, and g is 9.8, the acceleration of gravity. So the force of gravity on an object is its weight. And so the weight of this is 9.8 newtons. Kilograms is not weight. Kilograms is not weight, but that's a whole other discussion, okay? Kilograms stays the same, whether you're in outer space, on the moon, here. It's the amount of stuff. It's the amount of stuff there is. Weight is the gravitational pull on the object. So this 1 kilogram thing weighs 0 in outer space and weighs something like 0.6 kilograms on the moon, or maybe 0.4, I don't remember, okay? And weighs maybe 8 kilograms on Jupiter. No, I'm saying kilograms, that's not right. So, but anyway, its weight is about 40% or 50% on the moon, and on Jupiter it's 8 times as much. And in space it's 0, but the mass doesn't change. So that's a whole other story though. Okay. So anyway, so we have 9.8 newtons down. So what are the components of this vector? So if we want to write the weight vector, say W. Everyone should be able to write that in component form. Can you write that vector in component form? Change in x is, change in y is, negative 9.8. That would be that vector in component form. Okay? These vectors. So we need, if we're gonna relate this vector to these vectors, we need the components of those vectors so we can isolate the vertical components so we can relate it to the 9.8, the weight vector. Just like the artwork question on last time. So we'll look at this one right here. So we've got a x component and a y component. So we've got the actual force vector of the wire, and then we've got its 2 components. Which of those 3 do we know what it is? We've got to know something to make some progress here. Do we know the tension in the wire? Do we know the x component of it, or do we want to know the y component of it? I heard why. Why? How do we know why?
Because it drops 4 meters.
What's that?
Because the
Oh no, but these are force vectors.
it drops down 4 meters, so it's the distance from the from where the object is to the top of to the beginning of the wire is 4 meters.
Yeah, but these are force vectors. That's displacement. So yeah, you're right. So we've got 4 meters as displacement. So we could make a displacement vector triangle here. It'd be 4, 6, and then what? Square root of 52. Is that right? 36 and 16. So yeah, so that would be a displacement vector, but these are forces, right? So these are forces acting on that point. So which of these three, which component, or what do we know about the forces? Okay, yeah, what are you going to say? Right. The hypotenuse is 9.8? No, but it's in a different direction. See, so are you saying you're taking this 9.8 and saying that must be 9.8? No, because it's in a different direction. Just because it's down at 9.8, as soon as you start pulling it at some angle, then all bets are off. You can't say that that's 9.8 because it's going to be different depending on what angle this is pointing at. Okay, so Eitan, right?
Yep.
Last day, got it. Boom. All right. He said. So, what do you think? You think this vertical right here is what? Did you say you wanted to say what that was? 9.8. That's 9.8. Is that right? Not quite. There's 2 wires pulling on this point. They both add up to, the y components of the 2 forces in the wires will add up to 9.8. So this would be 9 point, that y coordinate would be 9.8 over 2. And that one over there would be 9.8 over 2. Or 4.9. So if you've got symmetry and you've got the cords pulling this way, and you know the downward force is 9.8, then the upward force of those 2 cords, or the wires, must be 4.9 each, balancing the downward 9.8. Doesn't make sense. So from that, so we have this displacement triangle, but then we also have a force triangle. And in the force triangle, we know that that upward is 4.9. And what are we looking for? Yeah, we want to know this. We want to know the magnitude of that vector, because that'll be the tension in the wire. Less or more than 4.9? A lot more, right? To get that 4.9 up, if you're pulling almost sideways, you're going to have to pull really hard to get 4.9 up if it's going out to the sides like that. So, and you can see the relative magnitude of that is going to be like at least twice as much as that. So how are we going to get that? So we've got this relationship of distances, and then we have this relationship of forces. Yeah, so we have similar triangles. So the relative size of the displacement vectors is going to be the same as the relative sizes of the force vectors. So we can take 52. There's different ways to do this, but the size of our hypotenuse relative to the vertical is radical 52 over 4. And so we're going to take that much times 4.9. There's other ways to do it. But we want, so this is how much bigger that hypotenuse is than the vertical. So times 4.9. So I think that will be, and that will be the magnitude of that vector. It doesn't ask for the direction, right? So we can do square root of 52 divided by 4 times 9. No, times 4.9. Doesn't like that. All caps, I think. Try that. Green bar. Questions on this problem? So the name of the game is when you have lots of vectors all acting in a situation, get them all in their components. So you can add apples to apples, horizontal, oranges to oranges, vertical. And then if you need to recover a polar form, do it at the end. So we could get the angle too here, right? So how could we use triangle trig if we needed this angle right here?
Do the tangent.
Okay, so we could actually use anything we wanted. If we have this whole triangle here, all lengths of all these sides, we could use tangent, sine, or cosine. Doesn't matter. Okay, questions on this problem?
Actually, I have a question.
Yeah, please.
If we do that, would we be, is it just doctrine we stick with degrees, or do we do it in
So when you get these real-world triangle problems,
you just take it as
what's that?
just take it as it's in degrees all the time?
Well, it should have a unit on it. It should. I mean, if you're given an angle measure, it should tell you what the unit is. So you're not to make any assumptions. Sound like you wanted to say you need to assume something.
Well, no, I figured that because and they're just giving us displacements and saying we want to get an angle.
Yeah. So when you're like in the real world and you're like in construction and you're building things and you're working with triangles in the real world, degrees is conventional to use instead of radians. So yeah. So that's what you'll see mostly in these real world applications. Jed.
How can we put root 52 over 4 times 4.9 and now root 52 over 4 times x over 4?
You could say equals x over 4.9.
Oh.
That's what you're thinking. So I just went right to a calculation. I know this radical 52 over 4 is the size of that relative to that. So then I could just multiply by 4.9. But you're thinking equals x over 4.9. That's right. That's true. Yeah. Other questions? Okay, so get out your sheet. You have homework, right? So I asked you to kind of observe what was going on and make some conclusions. So we looked at one. If two vectors have the same direction, then this dot product ends up being just multiplying their two magnitudes together. Okay, what was another case in this story? Adam? Opposite direction. I think that's my last one down here. I don't know. I should have looked beforehand. Okay, here we go. Maybe. So let's get okay. So opposite direction. What are some other ones?
Perpendicular.
Perpendicular. Okay. What else? Yeah. Acute. So closer, like a small angle. And obtuse. Those are the 5 cases, right? So hopefully you've narrowed it down to those 5 cases. I think this last one is opposite. We'll see. Here we go. Nope. That's obtuse. Okay, so this last one I have is obtuse. They're such that A has a component in the opposite direction as B. And that would mean obtuse when tail to tail. And what did you find out about the dot product in that case? What was the conclusion if they made an obtuse angle?
Negative.
What's that?
Negative.
Okay, so the dot product ends up being negative. What else? There's another thing we can talk about. What about the magnitude of that negative number? What's that? Is it what? Well, it would depend on the angle. But we could compare it to. Let's see here if I can find another case here. There we go. Have opposite direction. What was it when they had opposite direction? Negative product of their magnitudes. You should have found that. Okay, there we go. Yeah, so it's the opposite of the product of their magnitude. Now let's talk about, so if they're directly opposite each other, it's going to be the opposite of the product of their magnitudes. Similar to if they're directly in the same direction, it's the positive product of their magnitudes. So what about obtuse? We said it's negative, but then what else could you say about it? What about the magnitude can you say? What's that? Someone said something.
Less than the next.
So not as great of a number as the product of their magnitudes. Adam. I think you got it backwards. Yeah, you got the right idea. Less than 0, but greater than this opposite. So like the least you can do, the worst you can do, the biggest negative you can get is if they point in the opposite direction. If it's obtuse, then it's going to be some number in between 0, but it's going to be negative, but less negative than negative product of their magnitudes. Okay? What about, we said acute. I think that's this one. Such that A has a component in the same direction as B. In other words, they're acute when tail to tail. What do you get for the dot product then? So now that we've kind of started talking about this, talk to the person next to you. What is going to be the result? What can you say, can you conclude when they make an acute angle when tail to tail? Go. Okay. What do we think? Let's see here. Riley, what did you say about this?
I said that it would be less than the product of the magnitudes but greater than 0.
He said a positive greater than 0, but less than the product of the magnitudes. What do you think? Is that what you said? Yeah, exactly right. Positive, but less than if they had the same direction. Or in other words, the product of the magnitudes. And so what's left? Okay, so when you're talking about vectors that are perpendicular, there's a special term for that. And that's called orthogonal. Orthogonal. When two vectors are perpendicular, it's called orthogonal. And so the reason we have a different term is when you get into higher dimensions, if you have vectors that are 4, 5, 6 components, we can't really model that in, it's difficult to model that in our three-dimensional world, okay? But you can still have orthogonality. You don't have, it's not really perpendicular anymore because it's like beyond the dimensions that we live in. But you can still have this idea of perpendicular, which so we call it orthogonal, okay? Orthogonal. What happens when they're orthogonal? Dot product is 0. We should have found out that the dot product was 0. Okay, so our goal here is to kind of put this all together and figure out what this number is about. When we put this all together, any conjectures? So this number that's the biggest, the product of the magnitudes when they're the same direction, then as we have acute angles, that dot product is less and less and less until we get to right angle, and then 0, and then when we have obtuse angles, negative all the way down to the greatest negative is the opposite of the product of their magnitudes. So what is this about? What is this about? Any ideas? Jad wants to try. Yeah.
How the angle changes as it goes through the rotation.
Okay, but if we're trying to make meaning out of this number, the result, the dot product. Does it? So what are we seeing? I mean, it's really, that number is really about this, right? We're always kind of comparing it to what you would get if you multiplied their magnitudes together. But then how does direction play into it? So let's go back and look at one of these first couple here. If I take 5, 0, and 4, 3, what was the dot product for this one? 20. So how is this the product of their magnitudes? How is this the product? It's the magnitude of this one, 5, times what? Times 4. And what is 4 of that second vector? What is 4? What does 4 have to do with this second vector? Change in x, which is how compared to the first vector? How does the change in x in the second vector of 4 compare to the first vector? Okay, I wasn't talking about magnitude. No, I'm not talking about magnitude. So what else must I be talking about? Okay, so how does that change of 4, the x component, compare to the vector that has length 5? I'm not talking about magnitude. I'm talking about direction. What? No. I'm talking about comparing this change in x of the second vector to the first vector. It's so easy it's hard, right? No, that's the magnitude. Talking about the direction. No, it's in the exact same direction. The magnitude of this, that plate that gives us 20, is the change in x, which is in the exact same direction as the first vector. They're both pointing straight to the right, to the 3 o'clock position. All right, let's try the next one. And then 3, 4. All right, what's the dot product of this one? 15, which is what? 5 times 3. What about the 3? Where does the 3 come from in this vector? Oh, I did 2. Sorry. Screwed that up. That's the worst vector I've drawn all day. Okay, so what's that? Oh, thank you. Yeah, they are. Just that one was bad. Okay, so what about where does the 3 come from in this vector? Change in x. How does it compare to our original vector? Same direction, right? The change of the 3 is coming from the part of the second vector that's what? In the same direction as the first one. And so what about when they're perpendicular? There's no part of that second vector that's in the direction of the first one. Therefore, 0. There's no part of the second vector that's in the direction of the first one. So this dot product is multiplication of the two magnitudes in as much as what? It's the products of the two magnitudes in as much as the vectors are in the same direction. Do you get it? And then if they're in as much as they're in opposite directions, then you get a negative value. Okay, so how about this one? 3, 4, and 4, 3. So relative, so we know 25 is, all these are magnitudes of 5. So the biggest we can get is 25. How about this one? Just, compared to 25, is it going to be pretty close to 25 or not very close to 25? Pretty close. Why? Because they're almost in the same direction. So a lot of that second vector is in the same direction as the first. So now instead of comparing it to the x-axis, what are we doing? We're comparing it to the direction of this one. Right? So you have this direction of the first one. So almost all of that second vector projects onto the first one. And so you're going to have something, what do you get? What do you get? 24. Why? Because they're almost in the same direction. So you're almost getting just a true multiplication of their magnitudes. All right, so that's how I've summarized that here. The value of the dot product is the product of the vector's magnitudes. That's in general what it is, but only in as much as they are in the same direction. Okay, so that brings up a really important principle that we've seen. So, say this is 7. And I don't know, this is, what? 2.52. So how much of this second vector is in the direction of the first one? 2.5. What would be another way to get that? What would be another way to get? So what we're asking is, for that second vector, we're interested in that right there. What is another way of thinking about that amount, or that length, of the second one in the direction of the first one? Does anyone? What does it have to do with cosine? Yeah? I think he's onto something, right? So if we think about the angle between these two vectors, then this is what side of that triangle that's formed? Adjacent side. So this dot product has everything to do with cosine because we're taking the part of the second vector in the direction of the first. Well, that's the adjacent side of that second vector. Do you see? So, let's see. So I'm going to do this, change this to, no, that was fine. What did I have, 2.52? Okay, so that has some magnitude. How would we find the magnitude of this second vector? Right, so it'd be the square root of, so the magnitude of that, call that V, okay? So the magnitude of V is the square root of 2.5 squared plus 2 squared. Can someone do it real fast? What is that? So it's the square root of 10.25. Quick and loud. 2 exactly?
Yeah.
Let's do. There's got to be one more decimal place.
0.
Perfect. Okay. All right. So then, well, that's a more precise value than 3.2. All right. And then what's the magnitude of this one? So let's call this one, say, U. What's the magnitude of U? 7. Right? Everyone was thinking that. So if I have 3.2 here, and this one is 7, so we know the dot product. How could you compute the dot product of these two vectors? How do we get it? Using having the components? Multiply, like, and add, right? So it's 2.5 times 7. 17.5 is our dot product. And doesn't that equal, shouldn't that equal, that equals 7 times this red distance here. What's another way to write the red distance? So now we want to bring the angle into it. So how can we write that red distance? Cosine theta times 3.2, right? Isn't this adjacent side, isn't it 3.2 cosine theta? Cosine theta would be measured in radius lengths, and then we want that fraction of 3.2, right? So what does this give us? This now dot product gives us a way to relate to the angle between two vectors through cosine. Because we know that dot product is 17.5. It's how much in the same direction you get multiplied together. Well, another way to do that would be to take what? The magnitude of u times the magnitude of v times cosine of the angle. So here's another way to compute it, because what are we saying? We're saying it's product of the magnitudes in as much as they're in the same direction. Cosine is adjacent. So this is a way then, in this particular case, to solve, we could figure out what that angle is. We've got 17.5 divided by 7 by 3.2 equals cosine theta. So then what are we going to use? Our cosine? And let's get that number and see if it makes sense, right? So this is a first quadrant angle, right? We've got, everything's fine, so we don't have to make an adjustment once we get the answer. Should be exactly what our angle is. Anybody?
38.625.
38.625?
Yes.
I'll go with 6.3. Does it seem reasonable? 38 degrees. Does that look like it could be 30? Yeah, 45 is splitting, right? Splitting halfway up. It's a little bit less than that, 38.63. Okay, so two ways to find the dot product. The product of the magnitudes times the cosine of the angle between them, or which reflects that meaning that we were after. Okay, so this whole thing, product of the magnitudes as much as they are in the same direction. This new way of calculating it reflects the whole purpose of this sheet, to discover that. But both ways calculate it, and because of that, you can calculate, if you back calculate, you can figure out the angle between two vectors. Okay, so why don't you, while I take attendance, find the angle between, I'll pick one here, let's see. This one right here. Zero, -5, and 4, 3. Use dot product to figure out what the angle is between those two vectors. Okay? And I'll take attendance. Okay, so what's the magnitude of this one? 5. Magnitude of this one? Both 5. Okay, so 5 times 5 times the product of their magnitudes in as much as they're in the same direction. That's what dot product gives. The product of their magnitudes in as much as they're in the same direction equals, right? The easy way to calculate it. And what is that dot product? 0 times 4, negative 5 times 3, negative 15. So we got cosine of theta equals negative 3/5, negative 15 over 25, is that right? And so then, what's that?
How'd you get negative 15?
How to get this?
Yeah.
Because the dot product now, we've got two ways to calculate it. The product of the magnitudes, cosine theta,
Right.
and then the way you did every single one on the sheet.
Okay.
Right? 0 times 4 plus negative 5 times 3. That's how you did every single one of these.
Okay.
Right? It should be the number in this box right here in your homework. Negative 15. So then we got negative 15 over 25. Theta equals. We got an obtuse angle. It's going to be a second quadrant angle, right? What'd you get? 126.9. Okay. One more web work. Gotta have homework on dot product. Get ready for the final. It'll be due Monday at 5. It's due Monday at 5, and then the exam is Tuesday night at 7. PSF 166.
So the angle is going to be positive? Situation with the
It'll be a number between 0 and 180. The smaller of the two, right? Smaller angle, 0 and 180.